All right, so here's a bit of technique for machine learning, which I got from one of these textbooks, the Hands-on Machine Learning book. And this shows the difficulty of feeding data in. And also the thing I thought was very helpful is it helps show the human judgment that is still involved in machine learning. So first you just need to make sure you have the right versions of packages available, and we do in Colab. So just launching Colab, and I'm going to make a new notebook. All right, and this code here, we'll just import some libraries and print out version numbers, so it's not very interesting. This is where you start getting interesting stuff. Now, this is a database of California housing prices. They have districts of the state, regions of the state, and they have the price houses sold at and a bunch of other data to go along with it. So this will import that data from this GitHub repository, and then it will print a summary of the data. So we can see what kind of data we got to work with. And this is the point of this project is how to deal with data. And you see the data is kind of complicated. You got latitude and longitude, you got the total rooms and total bedrooms population, number of households, and then some object called ocean proximity that's not even a number. So you have a table of data, and the thing is, how would you prepare this data? So you can see an example of what the data looks like by using the head method that'll show you the first 5 rows of data. All right, and so latitude and longitude, you see total rooms and bedrooms and the median house value in the area. And here's the ocean proximity, which is near bay. Apparently that's just an alphabetical column giving you some information about where the houses are. All right. And so we can now get categories and counts with this counts value counts function. To get an idea of what's going on with that ocean proximity field, it has these 5 values with those counts. And you can get summary statistics with describe. And all these things, help guide you in deciding what kind of relationships between these variables would be worth investigating with machine learning. So here you get mean, standard deviation, and all that jazz for all those fields, although it clearly can't do any of that for the last field, which is not here. It can only do that for numeric fields. All right, and then you can make histograms. Oops. So it's going to make a histogram of all the various parameters. So I imagine. There it comes. All right. So now you can see, for example, that latitude and longitude are not evenly distributed or Gaussian. Of course, there's a big peak in Northern California and another big peak in Southern California. And here's median age, which is also a sort of complicated thing. Notice there's some kind of maximum here, a big pileup of things at the maximum, which is probably some kind of artifact in the data. And Again, also house value seems to hit some kind of maximum and have an artificial peak of data there. So this is the kind of thing. You see defects in data, which have to do with your, which you have to consider whether you really want to train on that or not. And here is creating training and test sets to work with. Same thing we've done in previous challenges. So this one here is going to take the training set and split it. So it's going to print out information about how long they are. It's going to take 20% of it to make test data and use the 80% of it as training data. So here you are. Now here's the head of the test set. You see you've got the first 5 records. And here's, so the training set is 16,000 records. The test set is 4,000 records. So we've done that. Now, here you get an issue of biased sampling. So if you consider this, just for comparison, let's suppose we have some kind of thing we're measuring that depends on whether you're female or male. And 51% of the population is female and the rest are male. If this is the case, if you do random sampling, you might end up with a biased sample. So here, we make a random sampling, and then we plot a histogram of it to see how many females there are in our sample. And you see, the population at large has 51% females, but there, if you do a random sample, you might get a different number. Your sample might have 49 or 48% or 53% females in it, and if that's important, your sample might not be representative of the whole. And by the way, there seems to be some kind of defect here. Oh, the splitting, I think, included a random factor, so you may not see exactly what I saw here. Anyway, so to avoid this, you do stratified sampling. You divide the group into subgroups called strata, and then you take exactly the right number from each stratum. So here, we make these categories for median income. And then we do a stratified sample. So this will define appropriate strata and chart them. So here's the number of people, number of records in various categories of the input data. Those are the strata, and now we can make stratified samples. So we split the data with this strat system, stratify housing. And so now, the training set has 35% in this category and 31% in that, and so does your test set. You carefully choose not random samples, but samples randomly out of each stratum, so the percentage of members in each stratum will be the same. And this is very much what you have to do in polling when you're trying to predict who the next president is going to be. It's exactly the same issue. They don't just use random samples. They use these stratified samples or adjust to them to get a more accurate result. And here's what would have happened if we used unstratified samples. For unstratified data, 2 of the train set has an error. Well, I'm about to do that one, so let's see. Oh, that's interesting. Income cat. Key error income cat. That's interesting. Worked fine here. Well, we're going to remove that column, but I guess we can remove it and verify it's gone, and then come back. It'd be the simplest answer. This one's not using the income cat column. That's very curious, though, why that happened. Let's try removing that column. I don't understand why it used to work and now it doesn't work, but this removes the column. I wonder if this stuff will run now. Well, wait a minute now. Oh, we just shouldn't be printing the income cat value. Oh, no, I see. We need it to make the counts to see how wrong it is. Yeah, I don't know what happened there. Yeah, but we do need it here, and it doesn't like key error. Yeah, okay, anyway, you don't really need that one. That's bizarre. But anyway, the interesting thing is to visualize the data. Weird, all right? Okay, so what we have here is latitude and longitude, and the way it's printed there, all the dots are running together. You can't see how dense the dots are in the dense area, so it's better to use transparent data. Here you've got an alpha of 0.2. If you use transparent data, you'll get a plot like this. And what's even better is to add more things in colors, like population and price. You get a much more informative view of the data. See, now you get a lot of information. And now you can see that you got a Northern California peak and a Southern California peak with high-priced homes, and the rural homes scattered all over the place. So there's just the kind of thing you have to do to plan things. So now the correlations are where you really get an opportunity to add human intelligence to your AI here. If you go here, then you can see which input parameters are correlated with the house value. House value is what we're trying to predict, and of course that's 100% correlated with housing value. But other parameters, most of these have no significant correlation. Income has a huge one, 68%. Total rooms and housing median age to some extent, and households. And if you make scatter plots, you can get more information about what kind of relationships exist between the data. Okay, so the ones in the corner are just histograms of housing value, but this is housing value versus median income. The strongest correlation we had, and you can see that as income goes up, housing price goes up, but you can also see weird artifacts. There's some kind of cluster of dots at the top indicating some kind of maximum housing value. There's another cluster here and another cluster here, sort of suggesting that the housing value has been rounded off or something. And I think there are a couple other things to notice here. So housing value, income has a large effect, and the other two parameters have a very little effect. These two have some correlation, but it's not very strong. And this will give us a more detailed plot. All right, here you can see more clearly the strange cluster of dots here and there that look like weird artifacts, and it might be good to remove that data. That data might do more harm than good. And here is something you often have to do. The input data parameters are not as predictive as combinations of those parameters. So here's a few combinations to try. We're going to calculate rooms per house bedrooms ratio, which is total number of bedrooms over total rooms, and people per house, seeing if those parameters are more correlated. And you see they are. Rooms per house is 14%, total rooms, housing median age. Rooms per house looks like a valuable combination of parameters to predict on. And here you can create those columns and calculate the correlations. Isn't that what we just did? I guess we didn't create the columns. All right. Yeah, this will create new columns in the housing table. All right, and there's more in the book, but that's it. This is the kind of data manipulation that shows how you modify the data before learning, and therefore human judgment is involved. So it really is kind of an art. And this is very much like what we're doing, where we have to add human intelligence to the machine intelligence to get good answers. So I thought it was worth going through. It takes me back to my database analysis days. So I'll stop this one. All right, and that's